Hello everyone, you already mentioned the title of my talk. I want to directly proceed to the motivation slide here. So magnetic force microscopy, you may be more or less familiar with this method. So it's a measurement of magnetic quantities, with a cantilever tip probe, and you can map these quantities with high spatial resolution. But disadvantage of many systems is that it's generally a qualitative method. So in this talk, I want to show the simultaneous stray field mapping and the perpendicular stray field derivative mapping with a special cantilever design and cantilever probe design. And this is based on a novel hybrid multimodal MFM approach. And this new concept, which is connecting a special cantilever beam design and a magnetic nanowire probe. And I want to show data as application to a bulk sample, which is hexagonal magnetic nickel gallium crystal, which has 001 easy access anisotropy. Okay, so why do we need nanowire based MFM sensors? So I show you here, this is nanowire, magnetic nanowire with a shell. In our case, it's a carbon nanotube. And with this magnetic nanowire, you can map sample surface and stray fields to map magnetic textures. And in a case where you have a very high aspect ratio magnetic nanowire, this pole behaves like a monopole because the other pole is very far away. So you can map this as an ideal point charge QT. And with this point charge, you can link the force which is measured by the cantilever directly to the perpendicular stray field components. This is so the limits of this monopole-like picture is depicted in CDEF, where you see, here we have a short nanowire where the pole is also giving stray fields and affects the outcome. Here in D, we have an extended monopole, so a smeared out monopole on this free end here. Then it can happen that if the diameter is too high, then we have a ground state which has a vortex here, and this is also not ideally point charge like in F. If you have an external magnetic field applied, we can also have internal magnetization which is deviating from the easy axis. So which is not good for our purpose. And we check this with micromagnetic simulations, and this is in the next slide here. And for a 20 nanometer cross section, we have nice accordance and a nice homogeneous magnetization. So this is a nice probe. And what we also checked is we took this in 20 nanometer cross section, the circular cross section. And here we see a magnetic pattern, which is periodic in X direction. And we can do Fourier analysis and check the accordance level of our monopole picture. And for this, we developed a new formula here where you can link the accordance level for different spatial wavelengths. And the outcome is that for our magnetic nanowire with 20 nanometer cross section and length 5 micrometer, we have nice accordance level for magnetic pattern with spatial wavelengths of 100 nanometer to 10 micrometer. So it's a very good value. Okay, so now how is it fabricated? Here you see a picket-shaped nanoworld TL1 cantilever with 500 micrometer length. Here we did some special cutting. Here this U-shape, reverse U-shape. And this is for bringing down the static mode cantilever stiffness, which is in the range of millinewton per meter. And this is used for measuring the deflection. So it's a very sensitive deflection measurement for low forces. And this is the magnetic nanowire encapsulated in a carbon nanotube, which is glued by e-beam assisted carbon deposition onto the cantilever. And what we see here is some confirmation from low-end stem measurements that indeed this tip has a monopole-like stray field pattern. So this is a nice probe. Okay, next slide. So how is this implemented? Yeah, in principle, this measurement mode can be employed for any customizable SPM microscope equipment. It can be upgraded, and the sensor can be also used in any equipment. The only need is an additional lock-in amplifier to guarantee this multi-frequency operation. And yeah, so here we see the static mode is reserved for the magnetic field measurement, and the frequency shift of the second mode is reserved for the field derivative measurement. And the high frequency mode, the fifth oscillation mode, is reserved for the distance control. And yeah, the amplitude is kept constant by a tip sample distance control. So here we see some data. So this is the magnesium nickel gallium crystal, which has 001 easy axis anisotropy, and the easy axis is pointing in your direction. And here we see some bubbles, and yeah, this is the magnetic channel. This is all recorded at one go. So in 100 minutes, we got this image with the different channels, and this is the perpendicular magnetic field, the stray field, and this is the perpendicular field derivative. So what we did is, yeah, we selected this bubble, did some radial averaging, and yeah, here we get this data, and we can fit various models. In the first case, monopole fit, and the second is the dipole fit. And we see here the accordance level is better for the monopole fit in both cases. So that means that we have a monopole-like field source in the sample. And I can now show you how this looks. Yes, okay. We can see in the third dimension, in principle, by checking this fits. And here, yeah, we can do a two monopole fit with variable diameter here of the bubble cross section, and with a variable height, so which is extending into the bulk. And in our case, yeah, h is going to infinity. That means we have a really nice monopole-like field source, and we can say this is like a magnetic flux tube, which is proliferated or elongated into the bulk. So, and we check this not only for one bubbles, but for 10 bubbles with a circle averaging. And yeah, this shows these global fits also show that the monopole model is more suitable. We have nice confirmation that we indeed have a pure monopole-like behavior of the bubbles, and yeah, some elongated structure into the bulk. So we can also get values. So the diameters range from 120 nanometers to 200 nanometers, which is a nice confirmation. Low-end measurements on thin film samples showed somewhat less diameters, but in the same range, so up to 100 nanometers. So we can also measure the burial depth, the burial depth of the top hole, so which is from 70 nanometers to 110 nanometers. With this slide, I want to show, acknowledge our joint cooperation with the Max Planck Institute of Chemical Physics in Dresden, and thank all the team, all of the team members from IFW. And I want also to thank you for your attention.